covalent bond is formed when two atoms share electron pairs from the valence shells, um, such that both the nuclei can then claim all the shared electrons to be their own in order to satisfy the octet rule. So earlier on we talked about the ionic bond model, where electrons are transferred, physically leave the valence shell of one atom to the valence shell of another atom, thereby making an actual cation and an actual anion that are attracted to each other. In covalent bonds, the electrons do not leave any of the valence shells of any of the atoms. What happens instead is the valence shells of the two atoms overlap each other, such that the electrons in those valence shells now have a larger space to move in around both the nuclei that are participating in this bonding. So if you look at these two atoms of hydrogen, where you've got the two nuclei of hydrogen in the middle, and then since hydrogen has only one electron, that electron is in the first shell. When these two hydrogen atoms come close enough to each other such that the shell of the first atom can physically overlap with the shell of the second atom, now those electrons have a larger space to move in. Now, such that the electrons now move around both the nuclei. So the sharing of electron pairs always happens by an overlap of valence shells of the two atoms that are undergoing covalent bonding. When you look at this covalent bonding of this kind, you notice that each electron can now each of the two nuclei can now count both of the electrons to be their own, and since it's the first shell, that's the valence shell, whose capacity is 2 electrons, both the nuclei are now satisfying the octet rule because they can both count the 2 electrons to be their own. So the octet rule in this case is satisfied by overlap of valence shells, such that those electrons can now be shared between the two nuclei. That ends up creating a covalent bond, and therefore creates a molecule this time, not a formula unit, but a molecule. The covalent bond is represented as this line over there that connects the two atoms. In this case, the two hydrogen atoms are being connected by a line. That line denotes a covalent bond. Each covalent bond, in other words, each of those lines indicates 2 shared electrons, or 1 pair of shared electrons. So every time one covalent bond is formed, 2 electrons have to be shared between 2 nuclei in order to create that bond. So let's look at some other molecules where covalent bonding is taking place. Please note in the previous slide that electrons did not leave either of the atoms and go to the other atom. There was no transfer of electrons, and neither was there a creation of a positive charge or a negative charge. So this ends up, the covalent bonding leads to formation of a molecule. Let's look at another scenario, another molecule, this time where 2 chlorine atoms are sharing electrons with each other. Now, if you remember correctly, the chlorine atom is in group 7A. In other words, each of the chlorine atoms have 7 valence electrons, and of course the octet rule says that atoms will either gain or lose or share electrons in order to have a full valence shell. In other words, 8 electrons in the valence shell unless the valence shell is 1, whose capacity is 2. Now in this case, chlorine, if you look at it, it's actually in the 3rd period, so the valence shell is the 3rd shell. In other words, 8 electrons. Each atom wants 8 electrons. So what they basically do is they decide to share electrons such that each chlorine atom is contributing 1 electron to that pair, such that they these two electrons get counted for both of the atoms. Now, if you look carefully in this molecule, each chlorine atom can really claim 8 electrons, thereby satisfying the octet rule. That's a molecule. This molecule is represented as Cl2 because 2 chlorine atoms made this unit. The covalent bond, once again, remember, is representing 2 shared electrons or one pair of shared electrons. This pair of shared electrons, of course, is known as the shared pair, or sometimes also known as the bonded electron pair. But chlorine had more than the electrons that were actually shared. Each of the chlorine atoms had 6 electrons that were not shared. Those remained on the individual chlorine atoms. Those do not get counted for the purpose of accounting for octet rule. So when you those electrons that are not being shared for the creation of the covalent bond are known as the lone pairs or the unshared pairs or the non-bonded pair of electrons. Please notice, when you're counting electrons to account for octet rule, those electrons do not get counted for both atoms. They only get counted for the atom that originally had them. It's only the shared electrons, the bonded electrons, that are counted for both atoms. So let's look at another molecule such as water. To go through this process again, to draw a structure that will allow us to explain the bonding in a molecule of water, there are 2 hydrogen atoms, and remember, each hydrogen atom has 1 electron. Its Z value is 1. Oxygen atom Z is valence electrons only, is in group 6A, therefore it has 6 valence electrons. Now each of the hydrogen, in order to fulfill the octet rule, requires 1 more electron, whereas oxygen, in order to satisfy the octet rule, requires 2 additional electrons. So neither of these elements is capable of donating an electron to another because each of those are non-metallic elements. Neither of these can make a cation. So instead of doing ionic bonding, they decide to share electrons. So there is 1 pair right there, which basically makes this hydrogen atom happy. This hydrogen atom now has 2 electrons, and then the other hydrogen atom can also share electrons, making that hydrogen happy. Go ahead and count the electrons now around oxygen, making sure you're counting all the shared electrons as well. So yes, oxygen is satisfying the octet rule as well because it has 8 electrons. So just to give you a count, 1, 2, 3, 4, 5, 6, 7, 8, also for oxygen. So all the 3 atoms are now satisfying octet rule, but we do need to rewrite this structure in a way that it shows the bonding clearly. Remember, each pair of shared electrons is 1 covalent bond. So 1 hydrogen atom has a single covalent bond between itself and oxygen, and the oxygen has another single bond between itself and the other hydrogen atom. A single bond is a covalent bond made up of 2 electrons or 1 pair of shared electrons. Now we're not done with the structure of water molecule yet, because oxygen, besides the shared electrons, also has lone pair of electrons that must be showed on oxygen atom because they stay on that atom. So the final structure of the molecule of oxygen can be given as such. This may be a good time for you to pause the video while you go ahead and draw the structures of these 3 molecules using the same idea. If you're done drawing the structures of these, hopefully you got ammonia as methane as an HCl, please remember that when you're drawing these structures, it's not just the bonds that you have to show, you must also show the lone pairs of electrons. Now these structures are called Lewis structures. We will not be going into the details of drawing Lewis structures, systematic method of drawing Lewis structures. We will also not be going into complicated structures which requires you to follow those principles of systematic drawing of such structures. We'll only be introducing the idea of covalent bonds and the different kinds of covalent bonds. So looking at very simple structures. Please also understand that Lewis structures do not give us any information about the orientation, three-dimensional shape of the molecule. In other words, basically what I'm saying is ammonia could have been also drawn as and still be the same. They are both the same. Similarly, I could have drawn water molecule instead of drawing the way I did. Like that, and that would also be correct. So Lewis structures do not really care about three-dimensional orientation. All they care about is, are the electrons being accounted for? In other words, when you are drawing these structures, you need to be sure that the total number of electrons that are shown in the structure equals the total number of valence electrons for all the atoms in the molecule. This is very important. For example, let's take the example of HCl. Now, HCl molecule is made up of hydrogen and chlorine. Hydrogen has 1 valence electron and chlorine has 7 valence electrons. So the total number of valence electrons is 8. In other words, when you draw the structure of this molecule, you need to show 8 electrons, not less, not more. And do we show them? So yes, absolutely. You've got 2, got 4, you've got 6, and you've got 8 electrons, so the structure is correct. Okay, let's go on to something different this time. Oxygen molecule. The oxygen gas that we breathe in does not exist as an atom. Instead, it exists as an O2 molecule. So what kind of a structure does this have? Once again, in order to draw the structures, we go back to the atoms. We know we have 2 oxygen atoms, and each oxygen atom has 6 valence electrons. And in addition to that, each oxygen atom needs 2 more electrons in order to satisfy the octet rule. But neither of them can donate an electron to the other because they're both nonmetallic elements. So instead, they share. They share 1 pair, but that only now gives each of the atoms 7 electrons. It's still not quite there yet. So how about we share another pair? If 2 pairs of electrons were shared between the 2 atoms, that would lead to 4 electrons being shared, which means 2 covalent bonds. It's a double covalent bonds when 2 pairs of electrons are being shared between 2 atoms. The structure, of course, is not yet complete because in addition to the bonds, each oxygen atom also has 2 lone pairs or 4 unshared electrons. Once again, please account for electrons. If each oxygen has 6 valence electrons, there should be 12 valence electrons shown in the structure. And if you count the number of electrons, let's see, 2, 4, 6, 8, 10, and 12. So yes, our structure is taking care of all the necessary electrons. Okay, go ahead and pause the video again and draw structures for these 3 remaining molecules shown. If you're done, you probably got carbon dioxide to look something like this, where there are 2 double bonds between carbon in the middle and 2 oxygens on either side and the corresponding lone pairs. This is formaldehyde, CH2O, and its structure can be drawn as like that. Once again, make sure all the electrons are taken care of, and since Lewis dot structure is not really does not really care about the shape of the molecule, you could have drawn it anyways as long as the correct atoms are connected to each other and the electrons are accounted for. Ethylene C2H4 has a double bond between the 2 carbon atoms, and each carbon atom in turn has single bonds to 2 hydrogen atoms. How about nitrogen gas? Nitrogen gas again is a diatomic molecule where two nitrogen atoms, each of which has 5 valence electrons, needs to now pair up their electrons in order to satisfy the octet rule. Let me try that again. I do not know what happened. So each nitrogen atom has 5 electrons, valence electrons I mean. In other words, our structure must show a total of 10 electrons. And now these are going to be shared. Once again, sharing one pair doesn't quite get to the point where the octet rule wants it to. Sharing another pair of electrons is not enough yet, so there is a third pair of electrons that is shared, which basically leads to a triple bond between the two nitrogen atoms, meaning 3 pairs of electrons are being shared between 2 nuclei, and then in addition to that, each nitrogen atom also has a lone pair, with showing a total of 10 electrons for the entire molecule. That is the structure of nitrogen molecule. Please pause the video and try out the remaining 2. Hopefully your HCN molecule, once you've drawn it, shows a structure like that. And then acetylene, which is a flammable gas used in blowtorches, looks like that. So covalent bonds can be single covalent bonds, double covalent bonds, or triple covalent bonds. There are no other higher degree of bonding that exists between such atoms. So let's look at some general trends. Look at all the molecules that you've drawn structures for so far and evaluate these trends. Number 1, non-metallic atoms will bond with each other via covalent bonding by sharing electrons in order to satisfy the octet rule. We have seen that. Number of electrons that each non-metallic atom will contribute for a covalent bond equals the number of covalent bond that it will form will equal the number of electrons that it needs in order to satisfy the octet rule. Let me say this one again. Let's take the example of hydrogen. Hydrogen atom already has 1 valence electrons, and according to octet rule, it needs to have 1 more. Because it needs 1 additional electron, hydrogen atom will only make 1 bond. Oxygen atom, on the other hand, has 6 valence electrons. It needs 2 more electrons to satisfy octet rule. So no matter which structure you look at, each oxygen atom will need to make 2 covalent bonds, either as a double bond or as 2 separate single bonds to the same atom. Similarly, nitrogen has 5 valence electrons, therefore it will need to make 3 covalent bonds in order to satisfy the octet rule. Once again, those 3 covalent bonds could either be as a triple bond, they could be as 1 double bond and 1 single bond, or 3 single bonds. So this way we can predict how many covalent bonds a certain non-metallic atom would need to make. Will equal the number of additional electrons that that atom needs in order to satisfy octet rule. The other very important trend that I hope you will notice is also that the central atom, the atom in the middle, needs to be the one that is capable of making most number of bonds. If you look at H2O, oxygen can make 2 bonds, hydrogen on the other hand only 1, so oxygen has to be in the middle. Ammonia, NH3, nitrogen can make 3 covalent bonds, hydrogen only 1, so nitrogen has to be in the middle. So any of those structures that you've drawn today, go ahead and make sure that you notice that the atom that is capable of making more number of covalent bonds will be the central atom. Okay, using these general trends, let's try and draw the simplest structures possible for compounds made when these non-metallic elements combine with each other. Go ahead, pause the recording, try it out on your own. When you do come back, hopefully you realize that iodine has 7 valence electrons, so it can make 1 covalent bond, whereas Nitrogen is in group 5A, and it needs 3 more electrons to satisfy octet rule, so it can make 3 covalent bonds. So if nitrogen can make more number of covalent bonds than iodine, then nitrogen should be in the middle. Now, since nitrogen needs to make 3 covalent bonds and iodine needs to make 1 covalent bond, how many iodines would you need so that iodines and nitrogen can all be happy? Exactly. You would need 3 iodine atoms to form 3 single covalent bonds with the same nitrogen atom so that the iodines are doing what they want to do and nitrogen is as well. However, please don't forget the lone pairs. Nitrogen originally had 5 valence electrons. It's used up 3 of them to make the 3 single covalent bonds. It still has a lone pair. Iodines, on the other hand, originally had 7 valence electrons, of which 1 is used per iodine atom to make the single bond. So each iodine atom still has 6 unshared electrons left over, or 3 lone pairs each. The final check also to do is look at your structure, make sure that every atom is now satisfying the octet rule. Okay, looking at carbon and chlorine, once again, since carbon can make 4 covalent bonds, it will be in the middle. Each chlorine will need to make 1 covalent bond, so we need 4 chlorines to bond with 1 carbon. Carbon originally came with 4 valence electrons. It's used up all its 4 valence electrons to make the bonds, doesn't have any lone pairs. Chlorines, on the other hand, came with 7 valence electrons and each only used 1 electron for sharing, so each still has 3 lone pairs. So finally, the structure of this compound will be CCl4. The molecular formula, the chemical formula of the first compound will be Ni3, and that for the second one will be CCl4.